Hello everyone, welcome to the 7th lecture of this course Heat Transfer. So today we will be discussing the conduction equation or the heat conduction equation in case of the unsteady state or transient state. So till now the heat conduction equations that we have discussed in case of one dimension or three dimension, and that is in case of the Cartesian, spherical or cylindrical coordinates. Those things we have discussed in case of the steady state heat conduction. Today we will be discussing the conduction equations in case of the unsteady state or transient state. Now before proceeding into this topic, we need to first discuss what is the difference in between the steady state and transient state or the unsteady state. So the difference in between the steady state and unsteady state, it can be discussed like this. That is, if the temperature of a body, it does not vary with time, that means it does not change with time, then that case it is known as the steady state. Now suppose if there is an abrupt or random change of the surface temperature of the body, so in that case what will happen, the body will attain an equilibrium temperature or the steady state after certain period of time. So during this period the temperature varies with time, and that body it is said to be in an unsteady or transient state. That means in case of an unsteady or transient state, the temperature of the body it varies with the time. So this is the basic difference in between the steady state and unsteady or transient state. Now this term transient or unsteady, it designates a phenomena which is time dependent. Now the steady state, it is thus the limit of transient temperature distribution for large values of time. Okay. Now this conduction of heat in unsteady state, which we will be discussing today, it refers to the transient conditions wherein the heat flow and the temperature distribution at any point of the system vary continuously with time. Now, what may be the applications or the examples of this unsteady state heat conduction? Like the cooling in case of the IC engine, that is the internal combustion engines. Next, the heating and cooling of metal billets, cooling and freezing of food, and heat treatment of metals by quenching. So all these things are the examples of the transient or unsteady state heat conduction. Now, during this unsteady state, the change in temperature, it may follow a periodic or non-periodic variation. So what are these periodic and non-periodic variations? So in case of a non-periodic transient state, the temperature at any point within the system, it varies non-linearly with time. Okay, so in case of the non-periodic variation or the non-periodic transient state, the temperature at any point within the system, it varies non-linearly with time, like the heating of an ingot in a furnace or cooling of bars or blanks in steel works, etc. So these are the example of non-periodic variation. Now, in case of a periodic transient state, the temperatures undergo periodic changes within the system, which are either regular or irregular, but it will be definitely cyclic because this is the periodic variation. So what may be the example of this periodic variation? These are cylinder of an IC engine or surface of earth during a period of 24 hours. So these are the periodic variations or periodic transient state. So this is the basic concept in case of the conduction of unsteady state or transient state. So today we'll be discussing the heat conduction equation in case of the unsteady state. Now till now we have considered the conductive heat transfer problems in which the temperatures are independent of time. So that is the steady state. Now in many applications the temperatures are varying with time, and in that case we require the understanding of the complete time history of the temperature variation for the system. For example, in case of the metallurgy that we have studied earlier, the heat treating process can be controlled to directly affect the characteristics of the processed materials. Annealing can soften metals and improve ductility. On the other hand, quenching, that is the rapid cool, can harden the strain boundary and increase the length. Now, in order to characterize this transient or unsteady behavior, a fully unsteady equation is needed. Now, in case of the three-dimension heat conduction equation, we know that del 2t del x2 plus del 2t del y2 plus del 2t del z2 plus q dot by k. This is equals to 1 by alpha del t del tau. So this is the three-dimensional heat conduction equation in Cartesian coordinates which we have discussed earlier. Now this alpha, this is k by rho c. This is known as the thermal diffusivity. It is the ratio of thermal conductivity to the heat capacity. And the unit of this thermal diffusivity is meter square per second. So all these things regarding this thermal diffusivity have been discussed earlier. Now in that equation we know that this q dot, this is the heat generation. Now without any heat generation and considering the spatial variation of temperature only in the x direction, so in that case the above three-dimensional equation, it can be reduced as 1 by alpha del t del tau, this will be equals to del 2t del x2 only, because we have considered the equation only in the x direction. Now for the solution of the above, we need two boundary conditions in x direction and one initial conditions. Now the boundary conditions, as the name implies, are frequently specified along the physical boundary of an object, and they can however also be internal. Example, a known temperature gradient at an internal line of symmetry. So considering this boundary condition and one initial condition, we can solve this one-dimensional heat conduction equation in case of a unsteady state. Now in this heat conduction in case of an unsteady state, there is one important parameter analysis that is known as the lumped parameter analysis or lumped heat capacity analysis. So what is that? So here it is written as internal resistance, it is L by Ka, and surface resistance, it is 1 by Ha. So what are these things? See, in case of all solids have a finite thermal conductivity, and there will be always a temperature gradient inside the solid whenever heat is added or removed. So that is fine. Now for solids of large thermal conductivity, in that case what will happen? If the solids are having large thermal conductivity, then with surface areas that are large in proportion to their volume like plates and thin metallic wires, the internal resistance, which can be represented mathematically as L by Ka, that internal resistance can be assumed to be small or negligible in comparison with the surface or convective resistance, which can be represented mathematically as 1 by Ha. So the examples of this type of condition when the internal resistance is assumed to be small or negligible in compared to the surface resistance or convective resistance are heat treatment of metals and time response of thermocouples and thermometers, etc. So in such cases, when the process in which the thermal resistance, the internal resistance, is assumed negligible in comparison with its surface resistance, it is called the Newtonian heating or cooling process. So what is this? In case of any solid body of large thermal conductivity, when its surface areas that are large in proportion or compared to their volume, like the plates and thin metallic wires, in that cases the internal resistance, these are assumed to be small or negligible compared to their surface or convective resistance. So this process, it is known as the Newtonian heating or cooling process. Now here we neglect the temperature distribution inside the solid, and here we only deal with the heat transfer between the solid and the ambient fluids. So in other words, you can say that we are assuming that the temperature inside the solid, it is constant and it is equal to the surface temperature. Now the temperature in this process is considered to be uniform at a given time. Now such kind of analysis, it is known as lumped parameter analysis or lumped capacity analysis, because the whole solid body whose energy at any time is a function of its temperature and total heat capacity is treated as one lump. Okay, so this is the main concept of lumped parameter analysis. So what happens here, there are two different resistances in case of a solid body that we have considered, which are internal resistance and surface resistance. So when the solid body is having a large thermal conductivity with surface areas which are large in proportion to their volume, like plates or thin metallic wires, so in that case the internal resistance of that solid body, it is assumed to be small or negligible compared to its surface resistance or convective resistance. Now this type of concept, it is known as the Newtonian heating or cooling process. Now the temperature in this process, it is considered to be uniform at a given amount of time or a given time period. Now such type of analysis, it is called the lumped parameter analysis. So here we assume that the temperature inside the solid, it is constant and it is equal to the surface temperature. Now let us consider a body whose initial temperature is Ti throughout and which is placed suddenly in ambient air or any liquid at a constant temperature Ta. This suffix A is for ambient and I is for initial, which can be seen in figure 1. Now the transient response of the body can be determined by relating its rate of change of internal energy with convective exchange at the surface, which we have discussed just now. In case of lumped parameter analysis, we consider the internal resistance. What we consider? We consider the internal resistance is very much negligible compared to the surface or convective resistance. Now here you can see the equivalent thermal circuit for lumped capacitance solid. Here the thermal resistance, it is 1 by HA, which can be seen in figure 1b. Now in this case the Q, this is equals to minus rho Vc dt d tau. This is equals to HA and the temperature gradient T minus Ta, which we will get from the Newton's law of cooling. Now in this equation 4.1, rho, it is the density of the solid, V, it is the volume of the solid body, C is the specific heat of the body, small h, it is the unit surface conductance, small t, it is the temperature of the body at any given time, As, it is the surface area of the considered body, Ta is the ambient temperature, and tau is the time. Now after rearranging the equation number 4.1, and if we integrate this one, then it can be represented integration dt divided by T minus TA. This is equals to minus HA by rho Vc integration d tau. This is the equation number 4.2. So this is a simple integration which can be written as ln T minus TA. This is equals to minus HA rho Vc and integration d tau. This will be equals to T only tau plus C1. This is the integration constant. Now here the boundary conditions we need to consider to find the value of the C1. So what are the boundary conditions? When the tau, that is the time, equals to 0, in that case the temperature of the body at any time, this will be equals to the initial surface temperature, which is T small I. So if we put this equation when tau equals to 0, T equals to Ti in the equation number 4.3, in that case we will get the value of the HA by rho Vc into tau. This part will be equals to 0 in the right hand side, and only the part C1 will be there in the right hand side of the equation 4.3, and in the left hand side it will be ln Ti minus Ta, because at the initial surface temperature Ti, this is equals to T as per the boundary condition considered. So we are getting the value of the integration constant C1 as ln Ti minus Ta. Now if we put this value of C1 in the equation number 4.3, then we are getting ln T minus Ta. This is equals to minus HAS divided by rho Vc multiplied by tau plus the value of C1. This is equals to ln Ti minus Ta. Now if we rearrange this equation, then we are getting T minus Ta divided by Ti minus Ta. This is equals to theta by theta I equals to e to the power minus HA divided by rho Vc into tau. So this is the equation 4.4 that we need to remember to solve the numerical. So this equation 4.4, it gives the temperature distribution in the body for Newtonian heating or cooling, and it indicates that the temperature rises exponentially with time. So this exponential heating and exponential cooling, it can be seen in the figure number 2. Now the quantity rho Vc by HAS that we are getting in the right hand side of the equation, it has the dimensions of time, and it is called the thermal time constant. So it is denoted by tau Th. Now its value is indicative of the rate of response of a system to a sudden change in its environmental temperature, that is how fast a body will respond to a change in the environmental temperature. So this is the physical significance of the thermal time constant. So it represents how fast a body will be responsive to a change in the environmental temperature. So this is the derivation of the equation of the lumped parameter analysis. So here we need to remember the basic concept of this lumped parameter analysis, that is for a solid of large thermal conductivity where the surface areas, these are very much large compared to their volume, like plates or thin metallic wire, then we consider the internal resistance is considered to be small or negligible compared to the convective or surface resistance. This type of process, it is known as Newtonian heating or cooling process, and here in this type of process it is considered to be uniform at a given amount of time, and this type of analysis, it is known as lumped parameter analysis. So this is the basic concept of this lumped parameter analysis. Now tau Th, this is equals to, that is the thermal constant, thermal time constant, that is equals to 1 by HAS multiplied by rho Vc. This is equals to RTH that we have seen from the thermal resistance diagram multiplied by CTH. Now this RTH is the resistance to convection heat transfer. It is equals to 1 by HAS. and Cth, this is equals to rho Vc. So this is the lump thermal capacitance of the solid. Now the earlier page, in case of figure 3, what we have seen, the transient temperature response. Here you can see that the thermal time constant, that is the tau Th, this is the multiplication of Rth and Cth. This is equals to rho Vc by Has. So here we can see that any increase of Rth or Cth, that is the resistance to convection heat transfer or the lumped thermal capacitance of solid, it will cause a solid to respond more slowly to changes in its thermal environment and will increase the time required to attain the thermal equilibrium, that is when theta equals to 0. Now this term HAS by rho Vc multiplied by tau, this can be represented as HLC by K multiplied by alpha tau by LC square, which is the equation number 4.5. Here alpha has been used, which is the thermal diffusivity of the solid, that is the ratio of thermal conductivity by heat capacity. Another terminology has been introduced here, which is the LC, this is the characteristic length. So what is this? This characteristic length, this is the volume of the solid divided by the surface area of the solid. So this characteristic length, it is the ratio of the volume of the solid body to the surface area of the solid body. Now we can represent the characteristic length in case of a flat plate by writing or by using the formulas of the volume of the solid body and the surface area of the solid body. So if we implement those formula, then we will get the value of the characteristic length as L by 2 in case of a flat plate. Now in case of a long cylinder, what will be the formula of the characteristic length, that is the LC, it is the ratio of its volume divided by the surface area. So the volume of a long cylinder is considered as pi r square L, it is known to us, and the surface area, it is 2 pi r L or pi dl if we consider the diameter. So the formula for the characteristic length, this is R, capital R by 2, where R is the radius of the cylinder. Now in case of a sphere, again if we write the volume and surface area of the sphere, then we will get the characteristic length as R by 3, where R is the radius of the sphere. Similarly, in case of a cube, we are getting the formula of the characteristic length as L by 6, where L is the side of the cube. So all these values of the characteristic length in case of a flat plate or cylinder or sphere or the cube, these are very much important in case of the MCQ type of question in the semester. So these are not very complex, we need to only remember the formula for the characteristic length. This is the ratio of the volume of the solid to the surface area of the solid. So if you can remember that much only, volume, ratio of the volume to the surface area, then we can calculate the characteristic length for any geometrical shape. So let us move to the next page. Now the last page we have seen in the equation number 4.5, the non-dimensional factor, that is HLC by K. This is known as the Biot number. It's a printing mistake, it is not Biot member, it is the Biot number. So it is a dimensionless term. Like in case of fluid mechanics, we have got a number of dimensionless parameter like Reynolds number, Froude number, Mach number, all these things. So this is another dimensionless term or dimensionless number. It is known as the Biot number, Bi. So the mathematical representation is HL by K, HLC by K. Now what is the physical significance of this Biot number? So it gives an indication of the ratio of internal resistance to the surface resistance. So it is the ratio of the internal resistance or internal conduction resistance to the surface resistance, which is the convection resistance or the convective resistance. Now, when the value of this Biot number it is small, in that case it indicates that the system has a small internal conduction resistance, that is relatively small temperature gradient or the existence of practically uniform temperature within the system. And the convective resistance, in that case, it predominates and the transient phenomenon is controlled by the convective heat exchange. Now, when this Biot number value it is less than 0.1, in that case, the lumped heat capacity approach can be used to advantage with simple shapes such as plates, cylinders, spheres, and cubes. The error associated is around 5%. So this value we need to remember to solve the numericals for the geometrical shapes. When the Biot number value we need to calculate first if it is coming less than 0.1. Now there is another dimensionless term which is alpha tau by LC square. This is known as the Fourier number. In case of conduction, the rate equation that we have got, that is the Fourier's law of heat conduction. Next, from the 3D heat conduction equation, there was one representation of the 3D heat conduction equation, that is the Fourier's equation. Now we are getting the Fourier number. So what is this Fourier number? Fourier number f naught, this is equals to alpha tau by LC square. So what is the physical significance of this Fourier number? It signifies the degree of penetration of heating or cooling effect through the solid body. Now, the final equation, it can be represented in terms of the Biot number and Fourier number, that is two dimensionless parameter, which can be written as theta by theta I, this is equals to t minus ta divided by ti minus ta, this is equals to e to the power minus Biot number multiplied by Fourier number. So this is another representation of the final equation in case of the lumped parameter analysis. Now, based on this concept of lumped parameter analysis, let us try to discuss some numerical. So what the question given, a 50 centimeter by 50 centimeter copper slab 6.25 millimeter thick has a uniform temperature of 300 degrees centigrade. Its temperature is suddenly lowered to 36 degrees centigrade. Now we need to calculate the time required for the plate to reach the temperature of 108 degrees centigrade. So given the rho equals to 9000 kg per meter cube, the value of C is given 0.38 kilojoule per kg degree centigrade, thermal conductivity is given 370 watt per meter degree centigrade, and small h thermal convective heat transfer coefficient, this is given as 90 watt per meter square degree centigrade. So we need to calculate the time required for the plate to reach the temperature of 108 degrees centigrade. That means the value of tau we need to calculate here. So that means to calculate the tau we need to use the equation of the lumped parameter analysis. So for that we need to first calculate some other things, that is the surface area of the plate, which will be equals to 2 multiplied by 0.5 into 0.5, that is in case of meter square unit. And get the volume of the plate we can also calculate. Then the characteristic length in case of the flat plate, so it is the ratio of the volume divided by the surface area. So these things we are getting 0.003125 meter. And what is the Biot number? The formula of the Biot number we have discussed just now, it is HLC by K. Now the value of H is given in the question 90, LC we have calculated just now, the characteristic length as 0.003125, and the value of K, that is thermal conductivity, it is also given in the question, that is 370. That means we are getting the value of Biot number is 7.6 into 10 to the power minus 4. Now the condition need to be applied here. Since the Biot number is less than 0.1 that we have discussed just now, so the value of the Biot number we are getting less than 0.1, so the lumped capacitance method or the lumped parameter analysis concept, it can be applied here to get the solution of the problem. So this is the equation for the lumped parameter analysis: T minus TA divided by Ti minus Ta equal to e to the power minus Ha divided by rho Vc multiplied by tau. That value of tau we need to calculate here. Now in this equation, the value of T, this is given in the question 108 degrees centigrade. The ambient temperature, this is also given 36 degrees centigrade. The value of Ti, it was given the initial temperature is 300 degrees centigrade in the question. The value of T again, it is 36. Now e to the power, the right hand side of this equation, e to the power minus Ha, the value of H is given in the question. A we have calculated here. The value of rho is given in the question 9000. Then the volume of the plate we have calculated, and the value of C, it was given in kilojoule per kg degree centigrade, which we have converted in joule per kg degree centigrade, multiplying this value by 1000. So only unknown variable here remaining, it is tau. Now from this equation we can easily calculate, as all the other things are known to us, so we can easily calculate from this equation the value of the time required for the plate to reach the temperature of 108 degrees centigrade. So the value finally we are getting here 154.32 seconds. So this is the final answer here. So what we have done here, we have only applied the lumped parameter analysis equation, and to apply that equation, one condition we need to check first, that is the value of the Biot number, it is less than 0.1 or not. If it is less than 0.1, then we are allowed to apply the equation for the lumped parameter analysis. Let's move to the next page. Okay. So a cylindrical ingot 10 cm diameter and 30 cm long, it passes through a heat treatment furnace which is 6 meter in length. Now the ingot must reach a temperature of 800 degrees centigrade before it comes out of the furnace. The furnace gas is at 1250 degrees centigrade and ingot initial temperature is 90 degrees centigrade. Now we need to calculate the maximum speed with which the ingot should move in the furnace to attain the required temperature. So the combined radiative and convective surface heat transfer coefficient is given 100 watt per meter square degree centigrade. The value of thermal conductivity, it is given 40 watt per meter degree centigrade, and the value of thermal diffusivity for the steel, it is given 1.16 in 10 to the power 5, 10 to the power minus 5 meters square per second. Now if we need to apply that lumped parameter analysis concept or that equation, then first we need to check the value of the Biot number. So to check the value of Biot number, which is the ratio of HLC by K, there the values of H and K, these are given in the question. That means we need to calculate the value of LC, that is the characteristic length. So the characteristic length, it is the ratio of the volume to the surface area of that body. So these formulas, these are known to us. That means we can calculate the characteristic length here for the cylindrical ingot. So the characteristic length value we are getting is 0.02143 meter. That means we can calculate the Biot number, as we know all the values of the H, LC and the K. So that means we are getting the value as 0.0536. So that means the value of the Biot number, it is less than 0.1. So that means the lumped parameter concept, where the internal thermal resistance is considered negligible compared to the surface resistance, it can be applied. So this is the equation of the lump parameter analysis, that is t minus ta divided by ti minus ta, this is equals to e to the power minus has divided by rho vc multiplied by tau. Now in the right hand side, that power part, e to the power that part, it can be represented like this here. That is alpha that is in terms of thermal diffusivity, alpha multiplied by h by k multiplied by a by v. That is another representation. If we represent that part in this way, then we can easily put the values which are given in the question. That means we are getting the value as 0.001353. Now if we put all these values in the above equation, then we can easily calculate the value of the tau, that is the time required, which we are getting 362.9 second. Now again we need to calculate the velocity of this ingot which is passing through the furnace. So what will be the velocity of that ingot? So from our basic concept, we can calculate the velocity, which is the furnace length divided by time. This is the formula for the velocity, length divided by time. The furnace length, it was given in the question, 6 meter, and the time that we have just now calculated, the value of tau, that is 362.9 second. So ultimately we are getting the velocity of the ingot passing through the furnace. This is equals to 0.01653 meter per second. So in this way we can calculate all these numericals related to the lump parameter analysis. So here, to implement or to apply the equation of the lump parameter analysis, we need to remember that we need to apply one condition, that is we need to check the value of the Biot number first. If it is coming less than 0.1, then we are allowed to implement the equation of the lump parameter analysis. Okay, so this is the end for today's lecture.